Greetings, Sir Janus. I am Renzo Tolentino, and I'm here to explain what are the contents of this main class we have. So, before I explain what are the contents of this main class, let me first explain the validation methods we use to validate the user inputs that are required for this class. So, first, we have a getValidInt method that identifies whether the string entered by the user is a valid integer or not. So inside this method, we have a try-catch block that identifies if the string entered by the user is a valid int. So inside this try-catch block tries to parse the or the string into an integer, and if it succeeds to do that, it will return the parsed string. And if it fails to parse the string entered by the user into an integer, it will be thrown into this catch block that displays an error message and return a zero value, which means that the string entered by the user is not a valid integer. So next method is this getValidString method, which is also the same as this getValidInt. So the only difference is the getValidString method checks whether the string entered by the user is a valid string. So this method accepts a string value and also returns a string value. It also have a try-catch block inside this method. So first, in this try block, this method tries to parse the string entered by the user into an integer, and if it succeeds to do that, it means that the string entered by the user is a number or an integer, and it will display an error message and it will return a null value, which means that the string entered by the user is not a valid string. So if this integer that parseInt method fails to parse the string into an int, it will be thrown into this catch block, which returns the string entered by the user, which means that the string is a valid string. So for the last validation method is this isStopExisting method. So this method checks if the stop or the location entered by the user, whether it's the pick up location or the drop off location, is a valid or existing location inside the city graph. So inside this method, we have a for loop that checks all the stop existing in the city graph. So if the current index or the current stop being checked is equals to the stop entered by the user, it will return the true, meaning that the stop entered by the user is inside or existing inside the city graph. And if this for loop ends or reach the end of its looping and still not find the stop entered by the user inside the city graph, which means that the location entered by the user is not existing in the city graph, and it will return to false. So after that validation methods explanation, let's go to the dummy data processing. So first, we imported all the packages needed in this method or in this class to perform the required operations. So first, we declare or we initialize the city graph passenger BST, the bus map that will be used to manipulate data inside this class. So we also have a passenger node called most urgent node, which stores the most urgent node found inside the passenger BST. We also have a bus node called nearest bus node, that stores the value of the nearest bus node for the current location of the passenger. So first, we have this. So inside the main method, we have this scanner class. You also have this integer, string, boolean variables that will be used later on for the user inputs. So first, this block here displays the header of the system. This method initialize the system, and let's go to this method. So this initialize system adds the bus stops, create routes, and register fleets inside the bus map, the city graph, and the passenger BSD. So first, this method calls the city graph that adds stop, which adds a stop into the city graph. So these methods are called 5 times to add stop A, B, C, D, and E. So next, this method calls the city graph that add route, or the distance between the pick up location or the start location and the end location. It also accepts a integer value that identifies the distance between these two locations. So this method are called 4 times that adds connection between stop A and B with a distance of 5 kilometers, distance between B and C, stop B and C with a distance of 7 kilometers, stop A and D with a distance of 10 kilometers, and lastly, distance D to E with a distance of 4 kilometers. So this part here adds a bus into the bus map, or register a bus into the bus map. So this bus map method requires a bus ID, a new bus that accepts the current location of the bus, and a boolean value that tells if the bus is currently available or not. So this method is called 3 times to add 3 new buses into the bus map. So the first bus with the ID of 1 and bus object that accepts a current location and a boolean value that tells if the bus is currently available. And fortunately, all the bus here are available. So let's go to the next method that is called inside the main method. So this receive passenger request is the method required or responsible to process the passenger request. This dummy data will be having. So inside this method, it have a header block, and the methods to insert the new passenger request into the passenger BSD. So first, the method that inserts the new request into the passenger BSD is this insert method that accepts a passenger object, which also accepts the name, the pick up location, the drop off location, and the urgency rate of each request. So going to the next method called inside this main method, this find most urgent passenger request, which identifies what is the most urgent passenger request recorded inside the passenger BSD. So to do this method, we need the most urgent node, which stores the most urgent node found, or the most urgent passenger request found inside the passenger BSD. So we identify the most urgent passenger request using this find most urgent method found inside the passenger BSD class. So this if block checks if the most urgent node is equals to null, meaning that there are no passenger request inside the passenger BSD. So if this most urgent node is not equals to null, it will then print a header block and displays the most urgent request data. So the data here displayed is the name of the passenger, the urgency rate of the passenger request, and its pick-up location and its drop-off location. So let's go to the next method called inside the main method, which is the find nearest bus available. So this method finds the nearest bus available nearest to the passenger current location or pickup location. So the nearest bus node is required in this step of the processing of dummy data. So this nearest bus node stores the nearest bus found inside the bus map. So to find the nearest bus inside the bus map, we use this find nearest bus method that accepts the pickup location of the passenger. So this find nearest bus method is found inside this bus map. So inside this method, we have this if block that checks if the nearest bus node is equals to null, meaning that there are no bus found nearest to the current location of the passenger, or if there are no bus recorded inside the bus map, and it will automatically or immediately return, meaning it will stop the execution of this method. But if the nearest bus node is not equals to null, it will assign the bus assigned to the bus found inside this or using this find nearest bus method. So going to the next method called in this main method is this calculate shortest path. So this method calculates the shortest path using Dijkstra's algorithm used inside the city graph. So inside this method, we have this display block that displays the distance from passenger current location from the nearest bus node current location to most or the passenger current location or pickup location. So if the bus current location is in stop A and the current location of the passenger is in stop B, it will print A to B. And it will automatically compute the total distance required to go from the bus location to the passenger's current location using this shortest path method inside this city graph class. So this display block also displays the distance between the passenger pickup location to the passenger drop-off location with the total distance will be traveled from his or her pickup location to drop-off location. And lastly, it will print or display the total distance from the pickup distance or the start up to the drop-off distance of the passenger. And this method, or inside this method, it will update the trip distance or the distance traveled by the user for this trip. So going to the next method called inside this main method, which is this dispatch bus. This method dispatches the bus and process the boarding of the passenger. So first, it will print the start, and next it will print the pickup location, which means that the passenger is picked up from his pickup location, and it will print that or it will print the short or the distance traveled by the passenger from his pickup location or from the current bus location to the passenger pickup location. It will then print the onboarding status or yes, its status, meaning that the passenger boards the bus. After that, it will print the distance from the pickup location of the passenger up to the drop-off location of the passenger. After that, the drop-off status is displayed, meaning that the passenger reached this drop-off location. And also, the nearest bus node, which is the bus assigned to pick up the passenger, will be set its availability to true. Also, the current location of the bus is updated, which is the drop-off location of the passenger. The passenger request data is also updated to trip dispatch and set its status to completed. The CityGraph completed trip count will also be updated once this dispatch bus is completed, and it will also print that the trip is completed, and it will display also that the bus used by the passenger is now available again. So the last method called inside this main method is this update summary. inside this update summary method, or this summary method is responsible for our for printing the report or the metrics of this system. So first, we have this pending request count, meaning it is the count of pending requests inside this system. So next, we have a header block for the summary report, and next we have the display of the total passenger request received by this system, that is count using this get passenger request count inside the passenger BS. We also have trips completed, that is printed or displayed using this get completed trip count method inside the CityGraph. We also count or displays the pending request using this display pending request method inside the passenger BSD. We also count the pending request count of the inside the passenger BSD using this get pending request count method. And also, we will print the average route distance traveled by the bus inside the system using this display distance average method inside the passenger BSD. So after that processing of the dummy data, we will now display a menu that lets the user to add, search, delete, display all passenger requests, display summary, and exit our program. So first, let's go to this add passenger request. So first, we have this while block that prints every time the option is not equal to 6, meaning if the option is equals to 6, meaning that the user wants to exit the program. So first, inside this while loop, we have a inner loop, which is this do while loop. Inside this do while loop, we display the menu, and we prompt the user to enter the choice, which are here. 1 for adding new passenger request, 2 for searching a passenger request, 3 for deleting a passenger request, 4 for displaying all passenger requests, 5 for displaying the summary, and 6 for exiting the program. So if the string input or the input of the user is stored in this input variable, which is a string, and read with this sc.nextLine method. So the input is get validated using this get valid int method that accepts a string that I explained earlier. So this get valid int will identify if the input is a valid int or not. So if this get valid int is not equals to 0, then it is a valid int. So this do while loop will run until the option is not equals to 0, or I mean this option is equals to 0, meaning that the choice entered by the user is not a valid integer. So let's go to the next part of this while loop, which is this switch case that identified the actions entered by the user. So for option 1 or case 1, which is adding new passenger request, it will first print a header, and it will ask for the passenger name stored in this passenger name variable. We also have a validation here that will validate all the inputs entered by the user. So for the first validation, for the first validation is for the pickup location. So just like the choice validation process, it is also the same as this three validation process. So first, it will check the input if it is a valid string, and if it is not a valid string, it will run until we get a valid string. And also, this stop existing method, which is a validation method I explained earlier, is returned to false. It will also run until the stop entered by the user is valid. The same process will also be performed in this pick up or drop off location validation process. So for the and also the same process will be performed for getting a valid urgency rate. So for case number 2, which is the search passenger request by ID, first it will be validated using this loop, and the main validation process is performed inside this get valid in method. So after this loop validates the ID or request ID by the user, the system will process and display the request the passenger request by ID using this display request by ID method that accepts an integer, which is the request ID to search. So this method is available at the passenger BSD class. So for case 3, it will delete a passenger request using the ID. So first, it will validate the request ID of the user of the it will validate the ID request ID entered by the user, and it will also validate the urgency rate entered by the user. And if these two inputs are validated and accepted, the system will delete the passenger request based on the request ID to search and its urgency rate using this delete method inside the passenger BSD method or class. So for case 4, it will just list all the passenger requests existing inside the passenger BSD using this display all request method. So, and next for the case 5, it will just print the summary or the metrics of the system using this update summary method, which I explained earlier. And for the last case, which is 6, using this case, it will close the program and display a thank you message.
Greetings Sarjanus, I am Max Altirimo, and for our project I will be explaining how our bus map class works. So our bus map implements a simple hash table for storing buses, validates bus stops against a city graph, and can find the nearest available bus. So first, import the city graph and the city graphs vertex list. So we will gonna be using this to verify stop names and compute the shortest paths later. And then next we have our class fields here. So we have an array called bus table. So this will store a bus node, and then next we have a integer called bus table size. So this will store the array length, and then next we have here a integer called available slot. So this will track the free slots, so we can decide when to expand the table. And finally, we have here a city graph and the vertex list. So we're gonna be using this to reference to the city structure used to validate locations and calculate distances. And then next we have here a class constructor. This so in this class constructor, we initialize the bus table array with the provided bucket list, and then we set the bus table size to bucket size and the available slot to bucket size also. And then we will gonna be storing the city graph and its vertex list to the class. And then next we have here a method called put. So the put method inserts a bus into the table, and then we declare the index and the start index, and then next the boolean is available for printing result. And then next we have here a if statement. This will validate if the bus's current location exists in the graph by calling is location existing, and then bus.get current location, and then if the location isn't in the graph, we will gonna be printing an error and return. And then next we have here another if statement. This validates if there are still unavailable slot, and then if the available slot is 0, we will call the resize bus table, and this will gonna be expanding the table. And then next we have here another if statement. This will validate if the bus ID of the bus is a integer, and then if it is not valid, it will display an error to the user. And then next we compute the index using the hash key method. This, and then we're gonna be storing the index at the at the start index. And then next we have here a while loop, and then inside the loop, if the slot contains a bus with the same ID, we print a warning, and we have a return statement. And then otherwise, we advance to the next procedure. We're gonna be computing the index of the next slot. And then if you look all the way back to the start index, using this if statement, it will gonna be printing a error message that will say there are no more slots available, and then we're gonna be resizing our table again. And then next we will have and the next, when we find an empty slot, we create a new bus node and store it in the bus table at the index that we calculated earlier. And then next is we will gonna be decrementing the available slot and print a success message with the bus ID, and with the bus ID, the stop and the availability here. The bus ID, the stop and the availability. And then next we have here a method called get. So the get method has a parameter of bus ID, and then it calls the search bus node with the parameter ID and returns the bus if found here, and returns null if not. Then next we have here a method called search bus node. So this node hashes the ID to find a starting index, and then codes linearly until it finds a matching ID here. Or returns to the start index, in which case it returns null. And then next we have here our hash key method. So our hash key ensures the key is non-negative by flipping the sign if needed, then returns the key modulo this dot bus table size. So this maps ID to indices in a simple way. And then next we have here a display all method. So the display all method iterates over the table and prints whether each slot is empty, or prints the bus ID and availability. And then next we have here a resize bus table. So the resize bus table doubles the table capacity, and then it copies the old table reference and create a new table of double size, and resets the available slots, and then reinserts each non-null bus node from the old table using put. method, and then next we have here a method called is location existing. So this method looks around the vertex list and checks whether any vertexes get stuck is equals to the location provided, and it returns true if found, and null I mean false if not. So this will help us to validate the bus stops. And then next we have here a method called find nearest bus. So this method scans all the buses in the table and uses the city graph, the shortest path with the parameter from and to compute the distance between from every bus's current location to the passenger's location. And then it ignores the buses that are not available, and then it tracks the smallest distance to return and the nearest available bus. And then next we have here a is valid int method. This method take a string and tries to parse it to an integer, and then if parsing succeeds, it returns true only if the integer is greater than 0, and otherwise false, and it catches a number format exception from non-numeric input. So that's all of our bus map class.
Dangal greetings, I am Jamel Cassandra A. Rustria, and in this part of the video, I will be explaining the bus class of the group's IPTMS. So this class serves as the blueprint for creating bus objects in the system. It contains 3 private attributes: the bus ID, current location, and is available, which is store a bus's ID, its present location, and availability status. So the class constructor for bus class initializes a new bus object by setting its location and availability, as we can see here in the parameter string current location and boolean is available. Next are the getter and setter methods for controlled access to each attribute. First, we have the getBusId, which returns the current value of bus ID, while the setBusId updates it with a new value passed to the method. This pattern of getters and setters are the same for the other attributes, which retrieves and updates the bus location and availability status. Through these methods, the class ensures proper encapsulation and safe data handling within the system.
Greetings, my name is Chilan Esteban from 283, and now I'll explain my part in our group project, which is the called bus node class. So the bus node class is we use it to keep the bus and its ID together. So the class has 2 private variables. The one is the key and the bus data. So the key is the ID of the ID number for the bus, and the bus data is object that has details like a bus location or if it's still available. And we made them private so the other parts of the program cannot change them directly and mess things up. And when we create a new bus node, we use the constructor bus node in key bus data. So this saves the key and the bus object into the node. Then it set in front bus data set bus ID key. So the bus also has the same ID as the node. So this makes sure the bus node and the bus objects match. And the class has also getters and setters. We can use get key and get bus data to safely to see the ID and bus info. So, and if we need to change them, we can use the set key or set bus data. And one thing to remember that if you can change the key with a set key, the bus object ID doesn't change automatically. So we have to update it ourselves to keep it the same. So basically, the bus node class is used to keep a bus ID and the bus info together. It helps us store, find, manage buses in the program in an organized way. That's all. Thank you.
Dangal greetings, Sir Janus. I am John Michael Achico from 2ITC. So, I am instructed to do and explain the city graph class. So, the city graph implements an undirected weighted graph of city stops, which is the vertices, and the routes, which is the edges. So here, this line declares a private field, which is the vertex list that stores all the stops vertices in the graph. It uses also a custom class vertex list that acts like a container that holds all the vertex node objects. So for the next one, which is the class field for displaying the system metrics. So also it is also a private field that has an integer data type, which is to keeps the track of the how many trips it have been completed in the system. It starts at also in 0, and this is the completed trip count. So for the next one, for the class constructor, which is the city graph, the city graph class, it is the constructor, and then the only job of it is only to initialize the graph by creating an empty vertex list so the graph can start storing stops vertices. So for the getter methods, it just only get the specific data, which is for the vertex list, and the get completed trip count variables. So for the next, I also added the add completed trip count method, which is to incrementing or adding the completed trip count. So for the next method, which is for adding the stop vertex to the root graph. So it has a parameter string and the variable stop, and the add stop method is just only to check if the stop is already exist in the graph, and if it does, it prints an error like this, and then if not, it creates a new vertex node which is with the stop name, and it will add into the vertex list, and it also prints a success message after adding it. So for the next method, let's proceed for the adding a root edges for between the two stops. So It also has a parameter string to from stop and to stop, and the integer variable, which integer data type, which is the variable distance. So the main purpose of it is just only to adding the root edges. So inside the method, first it will find the from the from and to stop. So if it is exist both of them, it will have the find stop method like this, find stop. So it will search it in the graph. So from the from vertex, it will search the from stop, and to the to vertex for the to stop. So this is the another value or variables for the from and to stop. So for the case 1 and the case 3, so here is only conditional statement that will only print if the stop is not found. So for the case 1, if both from vertex and to vertex is equals to null, which is they are not found, so it will print an error message, and also it will return just to return no return, but yeah. So for the case 2, if the from vertex is equals to null, just only from vertex, it will print that the from vertex or the starting vertex is not found, and it will also return. So for the case 3, vice versa, for the case 2, it will print an error message if the two vertex is null or not found in the graph. So for the case 4, if the newly added root edge is existing, so in here it will check if the newly added edges is existing. So if it is true, then it will show an error message that it is already existing. So for the case 5, so both stubs are found and add a new root. So it will check if the start and end vertex are found, then it will add a new root or edge is added in both directions. So from vertex, it will add to the to vertex, which is the destination, and to vertex from vertex, it will add in both directions. So it is like a graph with undirected. So after that, it will print a print success messages after implementation of it. So for us to know that it is processed. So for the next method, let's proceed to method for finding the vertex in the graph. So in here, I also added for finding the vertex. The only main purpose of it is just to find the vertex in the graph, and it uses for loop. In here, it uses for loop to ensure that all index will see in the method will run in the method. So all of the vertex will be shown. So for it to find the specific stop that the user will search, and it will also return null after finding it. So yeah. So next is for the method. Last but not the least is the shortest path method, which means purpose of it is to find the shortest path to the graph between the two stubs using the Dijkstra's algorithm. So first, let's find the start and end vertices. So for the starting vertex and the end vertex variables, they will find if the from stop and the end vertex to stop. Then it will proceed to the next next program, which is the if conditional statement. It will search if the starting vertex, or which is the start of the vertex, it will search if it is equals to null. Then it will also show an error message that the starting vertex, or the from stop, is not found in the graph, and it will return into 0. So for the next is vice versa for the starting vertex. If the end vertex is equals to null or not found in the graph, it will print a error message and then return it into 0. So for the variable number of stops, data type integer, it only get the size of the vertex list, and also create a variable for the shortest distance integers, and also for the boolean visited, and the integer array for the previous, and the variable number of stops inside the array. So in here, initializing the distance and visited. So for the for loop, inside of it is index is less than to number of stops. So for the inner, which is the shortest distance, and it will equals to the integer max value, and then the visited index, it will equals to the false, and previous index will be equal to the -1, which is the no previous vertex, which means of it. So next, so for the start index, which is the another variable integer data type, which is to get the vertex index of the starting vertex, and the integer variable end index, which is to get the end vertex. So it also makes the shortest distance, which is the start index, which it will equals to 0. We can see that always it starts in 0, so all the distances is equals to 0. Yeah. So here in the main Dijkstra loop, for in count plus plus. Yeah. So here it only shows the main Dijkstra loop, and then inside of it is to find the unvisited vertex with the smallest distance. So here we can see the nearest index, which is equals to the -1, the data type int. Also it is just to we didn't see, or we cannot see now the stop that we need to find, so we input this variable so that we can find it in the long run. So we also declare we also put the smallest distance, which is equals to the integer max value, which is the higher number or infinity, and inside. And next is for the for loop, which is for finding the smallest distance from the shortest distance, which is finding the visited with the nearest index. So it will always call the other stops, and it will be equals to the smallest distance. So if the nearest index will be equals to the -1, it will break, and it will say that no more reachable nodes. So visited nearest index will be equal to the true also, because it will be the final distance of the program. So here, after that, we will get the neighbors of the nearest stop, and so that we can see the other neighbors of the stop. So for the next one is to check if each of the neighbor is in the stop. So for this one, for the root, is equals to the neighbors that get vertex, and the vertex node neighbor stop, which will be equals to the root that get 2 vertex integer neighbor index, which is equals to get vertex index neighbor stop. So inside the for loop will be if conditional statement that visited neighbor index. So it's just simply adding the shortest distance to the root that get distance and equivalent to the new distance. So after that, it will have an if again conditional statement that finding the much better distance than the previous new distance. So after that, we finish the Dijkstra loop. So we proceed to the next to the process of the finding the shortest path. So next is for checking if end stop is reachable. So if each end stop is reachable, no path found from the 2 stop if the shortest distance and index is equal to the integer max value. So there's no, so it will return to 0. So reconstruct path from end to start. So in here, it will just show the reconstruction of the path from the end to start. So the string which has a variable name path, and the path length should be equals to 0. So in current index will be equals to end index, and the path length vertex list that get vertex, or simply just backtracking from end to start. So in here we can see that it will backtracking the way of the program in this part. So for the next one is for the print path in the correct order or reverse. It will print to the reverse because the previous loop is in the reverse order, so it will be reversed so that it will be corrected, and after that it will simply print the right order of the path. And for the last one, for the helper method, it is just only to get the vertex index of the vertex. That's all. Thank you.
Dangal greetings. My name is Nathaniel Gladys and I will be explaining the edge node class. So the edge node class is the fundamental building block used to define the weighted directed connection and edge between two nodes in a large graph structure. This class serves as a container for two essential pieces of information that define edge. Two vertex. This is a reference to the actual destination node, city graph, vertex node. In the graph, edges originate at a source node, that node containing this edge, and point to the vertex. Distance. This is integer weight assigned to the edge in a city graph. This weight logically represents distance or cost of traveling from source city to destination city. Primary function. The edge node objects are stored within the list that belongs to a city graph vertex. The source city constructor initializes the edge by setting both destination to vertex and the distance. Getters. The method get to the vertex and get distance allow the other parts of the graph program like search algorithm to easily access the way and connection destination and way. For example, if the city node for Chicago holds a list, this edge node object, the list represents all cities directly accessible from Chicago, and edge node is in that list. For example, two vertex next New York, distance 790. This means there is the edge starting from Chicago ending at New York with weight of 790. This structure in the core of adjacent list graph representation. Thank you. I'll be explaining the edge node. So the edge node is a fundamental data structure component used to represent a single route or connection between two cities. It serves two primary purposes. One is the destination reference. It holds the reference to the vertex node object that the route leads to. Number two is the route weight. Stores a distance or weight of that specific route, which is a crucial value for graph algorithm like Dijkstra's shortest path calculation. The key characteristics of this are the role represents an edge in the graph structure contained within. It is stored inside the edge list, which is itself owned by the vertex node. And the field is two vertex, a vertex node. Distance to an int, the weight and length of the road. In short, if you are at a city, a vertex node, an edge node in a city A, you simplify, tells the graph you can go to city B, the two vertex, the cost of 50 kilometers, which is the distance.
So hello, I'm John Paul Gabriel G. Panaligan from 2ITC. So let's go to vertex list. So now the fields. Fields is private vertex node, vertex list, private in size. We define two fields, vertex list and size. Size is an integer counter that tracks how many actual nodes you have currently stored in that array. The constructor, this is the vertex list equals new vertex node. Initialize our array with a starting capacity of 5 slots. This dot size equals 0 sets our counter to 0 because the list is currently empty. The add method, skipping the getters, let's look at the add method. This handles inserting new nodes. The very first line calls check capacity, We do not have before adding anything to ensure we don't crash the program by trying to put an item into a fully array. Once we have space, we place the new vertex into the array at the index equal to this dot size. So if else is 0, it goes in index 0. Finally, we increment size by the 1 to reflect that the list has grown. The check capacity method. Finally, the check capacity method. This handles the dynamic resizing. We check if size matches the arrays. If they're equal, it means the array is 100% full. Inside the statement, if the code logic is intended to handle the data transfer, we create a temporary reference to the current list and look through it. This block is where we would implement the logic to expand the array size and copy our existing data over to prevent an error. And that's it. Let's start with vertex node.java. This class represents a single location in our city graph. Private string stop, private edge list neighbors. At the top, we declare our private variable. First, string stop. This is the actual name of the vertex like Central Station or Main Street. Second, edge list neighbors. This is a reference to another class called edge list. It stores all the direct connections pointing out from the specific node. The constructor is the public vertex node string stop. Here is our constructor. It takes one argument, the name of the stop. Inside, we set this dot stop to the name passed in. Crucially, this dot neighbors equals new edge list. Initialize the list of neighbors as an empty object, so it's ready to have the edges added to it later. Below that, we have standard getters and setters. This allow other parts of our program to safely access or update the stop name and the neighbors list without accessing the private variables directly. Now, look at the hasEdge method. This is the logic center of this class. It takes a vertex node called destination as a parameter. For index equals 0, index neighbors.get size, index plus plus. We start a for loop. We initialize I to O and we keep looping as long as I is less than the size of our neighbors list. This ensures we check every single connection. If neighbors get vertex dot get to vertex equals destination, inside the loop we have this if statement. This chain of code is important. The number one is neighbors dot get vertex grabs the specific edge at the current index. Dot get to vertex, look at where the edge is pointing. Equals the destination, check if the endpoint is the specific destination we are looking for. If the match is found, we immediately return true, the edge exists. If the loop finished, checking every neighbors and find no match, we return false at the very end. This tells the system no direct route exists.
Good day everyone, I am Gio Perey and today I will explain the passenger BST class, which is a binary search tree designed to store, organize, and manage passenger requests based on their urgency rate. Now, let me give you an overview first. The passenger BST class is responsible for storing passenger requests in a binary search tree, organizing requests by urgency rate, handling duplicate urgency values using a queue system, displaying all requests or pending requests, finding the most urgent request, computing metrics like average distance traveled, and deleting completed requests from the tree. The main goal is to always keep the most urgent request easy to find and manage. Now let's move on to the class fields. Inside the class, we have several important fields. First is the root. This is the root of the BST. If root is null, the tree is empty. Next is the passenger request count. It counts how many total requests have been inserted. Pending request count. Count how many of those requests are still pending. request ID, which automatically generates a unique ID for each request. Average distance and total distance is used to compute the average travel distance of all passenger trips. These variables help the program track and measure passenger data. Next is the constructor. The constructor simply sets the route to null, meaning the tree starts empty. Next is the inserting a request. The main method to add new data is insert, which calls another method insert passenger node. So, how does insertion works? So first, if the current node is null, it creates a new passenger node. If the new request has a lower urgency, it goes to the left side. If urgency is higher, it goes to the right side. If the urgency is equal, the system forms a queue using the next pointer. This queue allows multiple passengers with the same urgency rate to be grouped together. Each inserted request also gets a unique request ID and a message is printed. Now let me discuss the handling duplicate urgency rates. If the urgency rate is the same as an existing node, the code walks through the .next linked nodes until it reaches the last one. A new node is added at the end. This creates a queue of equal priority requests stored at the same BST position. Now let's move on to the discussion of displaying all requests or display all requests method. The method display all requests print all requests in the entire tree. It uses recursion through the left subtree, the current node including any queued nodes, and the right subtree. This allows the tree to be displayed in sorted order based on urgency. Now let's move on to finding the most urgent requests. The method find most urgent returns the request with the highest urgency rate. Because high urgency values are stored on the right side of the tree, this method simply moves go right, right, right until no more right child. The last rightmost node is the most urgent one. Now let's move on to deleting a request. The delete operation works using the standard BST deletion rules. So we have case 1, which is a leaf node. If the node has no children, we will remove it directly. Case 2 is it has one child. In this case, we replace the node with its only child. Case 3 is we have the node has two children. In this case, we find the in-order successor, smallest value in the right subtree. Copy its key to the node, then delete the successor node. This ensures the BST remains valid. Now let's move on to displaying pending requests. The method display pending request prints only requests whose action status is pending. It again checks the current node, any queued .next nodes, left subtree, right subtree. It also updates pending request count. Now let's move on to the computing average distance. The method display distance average traverses the entire tree and adds trip distance of all requests into total distance. After the traversal, we get average distance by dividing total distance to passenger request count. This gives the average travel distance of all requests made. Now let's discuss the helper methods we defined. We have findMin method, which finds the smallest urgency value in a subtree, and it is used for deletion. We also have isEmpty method, which simply checks if the tree has no nodes. So to summarize, passenger BST is a binary search tree that organizes passenger requests by urgency. It supports duplicate urgency values using a linked list queue. It can insert requests, display all or pending requests, find the most urgent requests, delete completed requests, compute average distance. So the whole design is made so that urgent passengers are easy to track and process efficiently. So that's all for my part, and thank you for listening.
Mga Greetings and good morning, Sir Janos. My name is James Transerti Peralta, and I'm here to present my part, which is the passenger node data. So, at first, we encapsulated the private integer key, which represents the urgency rate of the passengers. And we also encapsulated here the passenger request class that has a request data left, right, and next. So what is request data? It contains all the passenger information like the name, pickup location, drop-off location, and urgency. And for the left and right, represents the left and right children of the binary search tree, and the next it just points to the next one. So we have here a class constructor that passenger node that has a parameter of passenger request and request data. As you want to see, the key here is getting the urgency rate, and we have here the getters and setters for the constructor encapsulated variables bulk. So we have here the public if get key, and it returns the key which is an integer value and sets the key that is only accepted at integer value, and here it returns the request data which contains the name, pickup location, drop-off location, and urgency rate. For the get next, let's return the next node and sets the next node. And for the left and right, it returns the left value of the binary search tree and sets the value of the left. And for the right, it's the same as the left. It just returns the right value of right children in the binary search tree and sets the right children in the right side of the binary search tree. Thank you, Sir Janos, and our greetings.
Greetings, I am Jewa Segunda, and now I'm gonna explain my part, which is the passenger request class. And it is basically the template we use every time a passenger sends a request in the system. Think of it like a form whenever someone asks for a ride, and we create one object of this class to store all their details. Inside it, we keep the passenger's name, where they will want to be picked up, where they're going, how urgent their request is, and lastly, what bus will be assigned to them. At first, the request starts with default settings like waiting for status and pending for action since nothing has been processed yet. The constructor sets this starting values automatically, so everything is neat and consistent from the moment the request is created. We also use getters and setters, which are safe ways to get or update the information inside the request. Instead of directly touching the variables, we use these methods to keep things organized and controlled. In short, this class helps us to keep track every passenger's request in a clean and structured way, making the whole system easier to manage. And that's all for my assigned part or task.